Hi everyone, welcome back. In today's video, we are going to talk about something every software architect and developer needs to know. The top 7 microservices design patterns for building better architectures. If you've ever worked on a microservices project, you know the challenges, things like service-to-service communication, database design, handling failures, or evolving your system without breaking everything. That's where design patterns come in. These are proven solutions to the most common problems teams face when building large-scale distributed systems. And in this video, we'll cover 7 of the most important ones. The API Gateway Pattern for managing requests, the Saga Pattern for handling distributed transactions, the Service Registry Pattern for service discovery, the CQRS Pattern for separating reads and writes, the database per microservice pattern for independent persistence, the event sourcing pattern for reliable state management, and the Strangler fig pattern for migrating legacy systems step by step. So let's dive right in. So what exactly is the API Gateway Pattern and why is it so important in modern application architecture? Let's break it down in plain English. Imagine you are building an e-commerce platform. You've got separate services for users, products, orders, and payments, each handling its own job. Your front end, maybe it's a website or a mobile app, needs to talk to all of them to make the app work. The front end has to get product data, authenticate users, place orders, and process payments. Now, without an API gateway, the front end would have to call each of those services directly. That means knowing multiple URLs, handling different request formats, dealing with different auth tokens, and managing all that logic right in the client. That's a mess. It creates tight coupling between your front end and all your back-end services. Every time a service changes, your front end has to change too. That's where the API gateway comes in. The API gateway acts like a smart middleman. It sits between your front end and all your back-end microservices. Instead of calling each service directly, the client talks to the gateway, and the gateway takes care of routing the request to the right service. But it does more than just forwarding traffic. It can handle authentication, transform requests, apply rate limits, log traffic, and even cache responses. It becomes a centralized layer of control for all communication coming into your system. Let's go back to that e-commerce example to see how this works in action. Say a customer opens your app, they browse the catalog, log in, add items to their cart, and check out. Here's what's really happening under the hood. When you have an API gateway in place, first the front end sends a login request to the gateway. The gateway forwards it to the user service, which checks credentials and returns a token. Next, the customer browses products. The front end sends a request like /API/products. The gateway knows that this should go to the product service, so it routes the request accordingly, maybe even adding a security header or logging the user ID for tracing. Later, when the customer checks out, the front end makes a single call to /API/checkout. But the gateway knows that this action involves multiple services: the cart, the inventory, the order, and the payment. So the gateway either coordinates those requests or hands them off to a back-end for front-end service that does. From the client's perspective, everything is simple and clean. Just one domain to call, one token to manage, one API contract to worry about, and if something changes behind the scenes, like the order service gets a new version or the payment service moves to another port, the client doesn't need to care. The gateway handles it all. Another key benefit of the API gateway pattern is security. Since all external traffic passes through a single point, you can enforce consistent authentication and authorization. You can add SSL termination, token validation, IP whitelisting, all without writing that logic in every service. And because the gateway sees all traffic, it's the perfect place to add monitoring, tracing, or request logs. That's critical when something goes wrong and you need to track down what happened. Now, of course, the API gateway itself becomes a critical piece of infrastructure. If it goes down, nothing gets in, so it has to be resilient, fast, and well monitored. and you need to avoid putting too much business logic into the gateway. Keep it focused on routing and cross-cutting concerns, not core service logic. So to wrap this up, the API gateway pattern solves a major challenge in distributed systems. It simplifies communication between clients and backend services, centralizes control, improves security, and gives you flexibility as your system grows. In any serious microservices architecture, especially in e-commerce where you have multiple moving parts, the API gateway isn't just helpful, it's essential. So let's talk about one of the most important patterns in distributed systems, the Saga pattern. If you've ever worked with microservices and tried to handle transactions across multiple services, you already know it's not easy. In a traditional monolithic app, it's simple. You just start a database transaction, perform a few steps, and either commit or roll back. But in a microservices setup, you don't have one shared database. You've got multiple services, each with their own database and logic running independently. This makes things tricky when you need a long-running transaction, something that spans across more than one service and needs to remain consistent. That's where the Saga pattern comes in. Let's break it down with a real-world example. Picture this. You are building an e-commerce platform. A customer places an order, and behind the scenes, several services need to kick into action. Here's the typical flow. First, the order service creates a new order in a pending state. Then it calls the inventory service to reserve the items. After that, it talks to the payment service to charge the customer. And finally, it confirms the order. Now, what happens if step 1 succeeds, step 2 succeeds, but step 3, the payment fails? You've already reserved the items, you've marked the order as created, but the payment didn't go through. So now you've got inconsistent data, a half-complete transaction spread across multiple systems. The Saga pattern fixes this by breaking the transaction into smaller local transactions, each handled by one service, and coordinating them using either choreography or orchestration. Let's use orchestration for this example. It's easier to follow in a video. So in our system, the order service plays the role of the orchestrator. When the customer clicks place order, the order service begins the Saga. It creates the order and then sends a command to the inventory service, reserve the items. The inventory service does its part. Maybe it reduces stock or marks the items as held. If that succeeds, the order service then calls the payment service to process the payment. But here's the important part. If anything fails along the way, like the payment fails due to insufficient funds, the orchestrator triggers compensating transactions to undo the previous steps. In this case, it would send a command to the inventory service to release the reserved stock, and it would update the order status to cancelled instead of confirmed. This way, the system stays consistent even though each service is managing its own data. No global lock, no distributed transactions, just smart coordination and undo steps. That's the core idea behind the Saga pattern, managing consistency through events and compensating actions rather than database locks. If you are working with microservices, and especially if you are building anything that looks like a workflow where actions depend on one another, learning the Saga pattern is critical. There are plenty of tools that can help implement it too. In the Java world, you might use Spring Boot with a message broker like Kafka or RabbitMQ, or orchestration engines like Camunda, Temporal, or Netflix Conductor. But the concept stays the same. Break the workflow into local steps, coordinate them with events or commands, and always have a plan for what to do if something fails. That's how you keep a distributed system strong, stable, and consistent, without giving up the flexibility that microservices give you. Hey everyone, welcome back. In this video, I'm going to explain something that quietly powers every microservices system you've ever used, from Amazon to Netflix. It's called the Service Discovery Pattern. This pattern solves a very real problem. How do services in a microservices architecture actually find each other when everything is constantly changing? To make it simple, we are going to walk through a real-world e-commerce example step by step. And by the end, you will know exactly what service discovery is, why it matters, and how it works behind the scenes. Let's get into it. Let's imagine you are building an online shopping platform. You've broken the system down into separate microservices. There is a product service that handles product details, a cart service that manages what users add to their cart, an order service that creates the final order, and a payment service that processes payments. Each of these services runs independently. They may even be written in different languages, deployed on different servers, and scaled differently depending on traffic. Now here's the issue. Let's say the cart service needs to talk to the product service. How does it find it? You might think just call its IP address, right? But in microservices that breaks down fast. Let's first see the problem and later we will see how service discovery solves the problem. Services in microservice systems don't stay in one place. They get restarted, they crash and restart automatically, they move to new machines, they scale up and down depending on traffic. So hard coding IP addresses or port numbers simply doesn't work. 1 minute the product service is at one address, the next it's somewhere else. And when you have multiple instances of the same service running for load balancing, which one should you call? This is where service discovery becomes critical. It solves the problem of finding and connecting to the right service, even when things keep changing. So here's how service discovery works and solve the problem. Every time a service starts up, let's say the payment service, it registers itself with a central system called a service registry. Think of the registry like a directory. It keeps track of which services are online, where they are, and what names they go by. Then when another service like the order service wants to talk to payment, it doesn't go looking randomly. It asks the registry, hey, where's the payment service? And the registry responds with the current location of one of its instances. That lookup is fast, it's dynamic, and it's accurate because the registry only holds data about services that are up and running. Let's walk through this in action using a real e-commerce flow. A customer adds a product to their cart. The cart service now needs to get the latest price and availability. It queries the product service. But instead of calling it directly, the cart service first asks the service registry, where's product service? The registry replies with a current IP and port of a healthy instance. The cart service connects and fetches the product info. Later, the customer proceeds to checkout. The order service is triggered. It needs to charge the customer's card, so it reaches out to the payment service. Again, it doesn't hard code anything. It asks the registry for the location of the payment service, connects to it, and completes the payment. All of this happens in real time and every service stays decoupled. No one needs to know where anyone else lives. They just ask when they need to. What happens? When services go down, let's say one instance of the payment service crashes. No problem. The registry has health checks in place. If it stops hearing from that instance, it marks it as unavailable and removes it from the list. So now, when the order service asks for payment, it only gets working instances. No broken links, no timeouts. This is where service discovery really shines. It lets your system recover gracefully from failures. You don't need to redeploy or manually update addresses. Everything adjusts automatically. This makes your system more reliable and much easier to scale. Now there are actually two ways to do service discovery. One is client side and the other is server side. In client side discovery, the service itself contacts the registry, picks a healthy instance, and makes the call. This gives you more flexibility and control. In server side discovery, the request goes through a load balancer or API gateway. That gateway talks to the registry and forwards the request to the right instance. Both are valid. Which one you use depends on your system design and tooling. But the core idea is the same. Services don't find each other manually. They register and discover each other dynamically. So that is all about service discovery pattern. Hey everyone, welcome back. Today I'm going to explain something that sounds complicated but isn't once you get it. It's called CQRS, which stands for Command Query Responsibility Segregation. By the end of this video, you will understand what CQRS is, when to use it, and why it's so helpful, even if you're just starting out as a developer. Let's get into it. Imagine you're building an online store something like Amazon. Now your app needs to do two things. First, it needs to change data, like when a customer adds a product to the cart or places an order. Second, it needs to read data, like when someone wants to see what's in their cart or check their past orders. Most apps try to do both using the same code and the same database. That works at first, but over time, it becomes messy. You are mixing read logic and write logic in the same place. Reads are supposed to be fast and simple. Writes are usually more complex. They need validation, business rules, maybe even transactions. This mix makes the code harder to understand and harder to scale. That's where CQRS comes in. Well, what is CQRS? CQRS is a simple idea. It says, let's separate the part of our system that writes data from the part that reads data. So we have one side called the command side that handles all the changes, like placing orders, adding items to the cart, or updating stock. And we have another side called the query side that only reads data, like showing products, orders, or recommendations. These two sides can use different models, different databases, or even different architectures because they have different jobs. Write side is focused on making sure business logic is followed. Read side is focused on performance and speed. Let's understand with real e-commerce example. Let's say a customer clicks add to cart. That triggers a command. The backend gets that command, checks if the product is in stock, then saves the cart item to the database. That's the write side. It handles changing the data. Now later the customer goes to view their cart. That's a query. The system looks up all the items in the cart and sends that list back to the user quickly and efficiently. That's the read side. It only reads, it doesn't change anything. With CQRS, we keep these two parts separate, so our code is cleaner and our system is easier to scale. Next, why is CQRS pattern useful? First, it improves performance. The read side can be super fast. Maybe it even uses a separate read-only database or a cache. It doesn't deal with heavy logic. It just fetches data and sends it back. Second, it improves flexibility. You can scale the read side differently from the write side. Maybe your reads are 100 times more frequent than writes. Now you don't need to scale everything, just the part that needs it. Third, it improves code clarity. When you look at your write logic, it's focused only on rules and validation. When you look at your read logic, it's focused only on queries and formatting. Now, should you use CQRS for every project? Probably not. If your app is small, a single database with simple reads and writes is fine. But if you are building something bigger with lots of users, lots of traffic or complex business rules, then CQRS becomes very helpful. Especially in systems with microservices or event-driven architecture, CQRS fits naturally. You can even start small. Use it for just one part of your system, like the checkout or the order history, and expand later. Now, one last question you might be wondering is, how do the read and write sides stay in sync? If we're writing data in one place and reading it from another, how do we make sure the read side actually shows the latest changes? Here's how it works. After a command is processed, let's say a customer places an order, the system sends out an event. That event might be something like order placed or cart item added. This event gets picked up by another part of the system, usually an event handler, and that handler updates the read model. So even though the command and query are separate, they're connected through these events. And this happens really fast, often within milliseconds. But technically it's not instant. It's called eventual consistency. So when a user places an order, the read model updates just after that. And when they check my orders, the new order is already there. That's the beauty of CQRS. You keep reads and writes clean and separate, but still in sync through smart messaging. Some teams use message brokers like Kafka or RabbitMQ. Others use internal event buses. Whatever tool you choose, the idea is the same. Write the data, emit an event, then update the read model. It's simple, fast, and scalable. Hey everyone, welcome back. Today we are going to talk about something you absolutely need to understand if you are working with microservices. And that's the database per microservice pattern. It's one of those core concepts that helps you avoid data chaos as your system grows. We're going to walk through what database per microservice pattern means, why it's important, and how it plays out in a real e-commerce platform, from browsing products to placing an order to making a payment. Let's get into it. So imagine you're building an e-commerce system, and like any good architecture these days, you are going with microservices. You've got a product service for managing inventory and product info, a cart service to handle items users add to their carts, an order service to actually place the order, and a payment service to handle transactions. Each one is small, focused, and independent. That's the beauty of microservices. Now here's the question. Where do they store their data? Should all these services talk to the same central database? It might sound convenient, but that's where things go wrong. Let's say all your services use one big shared database. Now your product service has its own tables. So does the cart service. Same with orders and payments. But since it's one database, nothing is truly isolated. One service could accidentally modify another service's data, or maybe you change a schema for one table, and suddenly another service breaks, even though it has nothing to do with that feature. You also end up with tight coupling. You can't scale services independently, you can't deploy them separately, and now you've got teams stepping on each other's toes, waiting for database migrations to finish. This is exactly what the database per microservice pattern solves. So what is database per microservice pattern? With database per microservice pattern, every microservice owns its own database. Fully, the product service talks only to its own database. The cart service, same. The order and payment services, they each get their own isolated database too. This creates a clean boundary. One service can't directly access another service's tables even if it wants to. If the product service changes its schema, that change has zero impact on the other services. This gives each service the freedom to evolve, scale, and deploy without waiting on others. Let's go step by step through how this works in your e-commerce system. A customer browses the store. The front end calls the product service to fetch a list of items. The product service pulls product data from its own database, things like name, price, and stock. Next, the customer adds an item to their cart. The cart service gets that request. It doesn't ask the product service for permission. It just adds an entry to the cart table in its own database, storing product ID and quantity. Now, the customer clicks checkout. That triggers the order service. The order service pulls the cart items from the cart service, but only via an API call. It doesn't access the cart database directly. It creates a new order in its own database and calls the payment service. The payment service handles the transaction and logs the payment in its private database. At no point does one service reach into another service's data layer. They communicate via APIs or events, but they never share the same database. So why is this so helpful? First, it isolates failure. If the product services database is down, it doesn't bring down the order or payment services. Second, it helps you scale. Let's say the cart service is getting hammered with traffic. You can scale just that service and its database. No impact on the rest of the system. Third, it makes development faster. Teams can work on their services independently. They don't have to sync on database migrations or fight over table locks. You get cleaner code, fewer bugs, and more flexibility. You might be wondering, what if two services need the same data? Let's say the payment service needs product pricing to confirm the final amount. In a monolith, you'd just join two tables. But in microservices with separate databases, you don't do joins. Instead, the payment service would either call the product service API to get the price, or listen to events like product price updated and keep a local copy of that data in its own database. This is called data duplication for autonomy. You copy just what you need and keep services decoupled. Yes, it's a little more effort, but it keeps your system clean, modular, and resilient. So to sum it up, the database. Per microservice pattern means every service manages its own database. No sharing, no cross-service queries, no accidental coupling. It helps you isolate failures, scale services independently, and move fast without tripping over other teams. If you have ever wondered how companies like Amazon track every action in an order and how they recover when something goes wrong, event sourcing is a pattern that makes it all possible. Let's understand the event sourcing pattern with an e-commerce platform use case. Let's say your e-commerce platform is built using microservices. You have an order service that creates and manages orders, a payment service that handles payments, an inventory service that manages product stock, and a shipping service that ships the product. Now imagine a customer named Sarah visits your store and places an order for a phone. In a traditional app, the order service might just update its database and change the status from new to paid to shipped. But in microservices and with event sourcing, that's not how it works. Instead of each service saving just the final state, each one records events for every action it performs. These events are the source of truth, and they are shared across the system. So here's how event sourcing pattern works. Sarah places an order. The order service saves an event called order placed. It doesn't save a full order record, it saves the action that happened. This event is published to an event store, a kind of log where all events go. Next, the inventory service picks up that order placed event. It checks if the phone is in stock. If everything looks good, it emits another event, stock reserved. Now the payment service listens for that. When it sees stock reserved, it charges Sarah's card and emits payment successful. Finally, the shipping service sees that payment was successful, prepares the package, and emits order shipped. All of these services are decoupled. They don't call each other directly, they react to events, and they emit new ones. That's the event sourcing approach. So now let's say the system crashes. You don't lose the order. Why? Because all the steps, order placed, stock reserved, payment successful, order shipped, were recorded in the event store. You can replay them one by one to rebuild the full order status. Start from nothing, apply order placed. Okay, we have a new order. Apply stock reserved. We know inventory was confirmed. Next, payment successful. The payment went through. Finally, order shipped. The phone is on its way. You didn't need to store any current state. You built it from events, and you can always do it again anytime. Why this pattern is powerful. Now let's say Sarah contacts support. She says she paid but never got her phone. Instead of guessing, your system shows the full story, not just the current status. You can see exactly what happened when the order was placed, if stock was reserved, whether payment succeeded, and whether the package was shipped. Everything is traceable because every step was captured as an event. You can debug problems, track delays, or even rewind and fix issues just by looking at the events. It also works great for analytics. Want to know how many orders were paid but never shipped? Just filter events. No need to query a big messy database. Why event sourcing pattern works so well in microservices? Well, event sourcing is especially useful in a microservices architecture. Services stay small and focused. They don't need to know how other services work. They just react to the events they care about and emit their own when something happens. The order service doesn't call the inventory service. It just emits order placed and moves on. The inventory service listens and reacts. Same for payment and shipping. This keeps the system loose and flexible and makes it easy to add new services without changing the old ones. You can even add a notification service that listens for order shipped and sends a confirmation email. No changes needed to the shipping service, just plug in and go. So to wrap up, event sourcing is a powerful pattern that works beautifully with microservices. Instead of saving state, each service saves events like order placed, payment successful, order shipped. These events are stored, shared, and used to build views, recover from failure, and track what really happened. In our e-commerce example, we followed Sarah's order through the order, inventory, payment, and shipping services, and saw how events made the whole process traceable and resilient. If this helped clarify event sourcing in a real system, give the video a like and subscribe for more real-world backend content. Hey everyone, welcome back. Today we are breaking down a pattern that's incredibly useful if you are trying to modernize legacy systems without going through painful rewrites. It's called the Strangler fig pattern, and yeah, it's named after a tree, but it actually solves one of the biggest problems in real-world software. How do you replace an old monolithic app with microservices without breaking everything? We are going to walk through it step by step using a real e-commerce example, and by the end, you will know exactly how and when to apply this pattern. Let's get started. Let's imagine your company has been running an e-commerce site for a few years. It started out as a big monolith. One code base, one database, one giant deployment. At first it worked fine, but now it's slow to scale, hard to maintain, and almost impossible to upgrade without causing problems somewhere else. You want to move to microservices, but doing a full rewrite, that's risky. It could take months, and if something goes wrong, your customers and your revenue suffer. That's where the Strangler fig pattern comes in. What is the idea behind Strangler fig pattern? Think of a real Strangler fig tree. It starts small, growing around the outside of an existing tree. Over time, the fig grows stronger, while the original tree weakens and fades away. The software version works the same way. Instead of replacing your entire monolith all at once, you slowly wrap it with new microservices. You take one feature at a time, like product search or order history, and rebuild that in a new service. Then you route traffic to the new service instead of the old one. Bit by bit, the monolith gets smaller. Eventually, it's either gone or small enough to manage without pain. So let's apply this to your e-commerce app. Your monolith handles everything: product listings, cart logic, checkout, payments, order tracking, reviews, and user accounts. You decide to start by pulling out the product catalog because it's high traffic, low risk, and doesn't depend on a lot of other services. You build a new product service, a standalone microservice that fetches product names, descriptions, prices, and images from its own database. Next, you update the API gateway or your routing layer. Now, when a user loads the homepage or browses categories, the request for product data goes to the new product service, not the old monolith. Everything else, like the cart and order placement, still runs through the monolith for now, but congratulations, you have just used the Strangler fig pattern. One feature has been safely migrated without touching the rest of the system. Now that you've gained confidence, you move on to the next feature. Maybe the reviews module. You build a dedicated review service. It owns its own database, handles customer feedback, and includes a clean API for the front end to use. Again, you update routing rules so that all review related requests go to the new service. Then maybe you do the same for the order history or the checkout flow or the user profile section. Each time you build one microservice, you isolate it from the monolith and you slowly reroute requests to the new service. You are not breaking the old system, you are replacing it piece by piece with something better. The reason the Strangler fig pattern works so well is because it reduces a risk. You don't freeze development for 6 months to rewrite everything. You keep your system running the entire time, and you only change what you understand. It also gives teams flexibility. Maybe the product team owns the product service, another team handles reviews. Everyone can work in parallel at their own speed. And because each new service is separate, you get all the benefits of microservices: faster deployments, independent scaling, and easier testing without crashing your legacy app. You might be wondering, what about the database? In many cases, the monolith has one massive database. When you extract a feature, you copy the relevant tables to a new service database, or you set up sync jobs or events or temporary read-through APIs. It depends on your setup, but the key rule is each new service owns its own data going forward. It doesn't reach into the monolith's database. And when you need to connect things like checking inventory while placing an order, you do that through APIs between services, not shared tables. That's how you slowly cut off the monolith's roots without chopping it down all at once. Eventually you reach a point where the monolith is barely doing anything. Most of the features have been moved out, most of the traffic is hitting the new services. At that point, the monolith can either be retired completely or kept around as a simple legacy admin tool or fallback system. And now your platform is fully microservices based. And you got there without the drama of a big rewrite. Thanks for watching, and I will see you in the next video.